Welcome to the course. Everybody, I see you're very numerous. There must be a deadline today. Today I'm going to talk about Erlang, really as an industrial strength tool. So I'm going to talk in two parts. So the first part, we will look at the behaviors, servers, and supervisors. And in the second part, I will give a talk actually given by a company called Demonware, who makes software for games. And this will give you a lot of practical ideas, okay? So last time we saw the philosophy of Erlang. Erlang's philosophy is, if something goes wrong, let it crash. Seems very counterintuitive, but actually works really well. And do not program defensively. Do not add checks. If your system goes wrong, just let it crash. And to make your application, Erlang has a platform, a set of libraries called OTP, Open Telecom Platform, which is available for the Erlang site, and it has behaviors. Behaviors are generic tools that let you build your application with only a little bit of work. There's servers, there's event handler. Finite state machine is like the code for your application, the internal code. Then there's the actual application, which is a group of things. And then there's the supervisor. This is for handling the errors and the restart. Today I want to talk about server and supervisor, and I show you how they are implemented, show you the code, really show you how it works. Okay, so behaviors hide complexity. They make your application code really simple, and even though it's simple, it's concurrent and fault tolerant and very nice. So these generic behaviors are really powerful. Okay, so that's what we saw last time, but this time we go to the next level. I'm going to start by showing you a generic server and how it works and how it's useful. So we're going to build a behavior. You can think of a behavior kind of like a design pattern, but a pattern for multi-agents. You saw maybe patterns in object-oriented programming. Patterns in object-oriented programming are simple things. They only do a little bit. But behaviors are like really big, powerful, very powerful patterns that work in multi-agent. And the platform OTP has a set of these behaviors, and so usually you use these, okay? So all the tricky stuff, all the messy stuff, is done in the behavior, so you don't have to worry about it, and it's tested and everything. So we're now in a university course, so I'm going to show you how to build a generic server behavior, okay? A server like for client server. So servers are used a lot. So this behavior is actually used a lot in an Erlang program. So we're going to go through some Erlang code, and I will explain to you how it works. Here is a very simple server in Erlang, okay? So you start it here, you spawn a process, which will be the server. It starts by doing an initialization with a certain set of arguments. So then you set up the server, okay? You init it, so you have some initial state. Servers have some internal state, maybe it's database, whatever state they have. And then the actual server is a loop, okay, loop. So this loop is basically just a recursive function. In Erlang, the loops are done using recursion, because Erlang internally is very functional. So you do loop, and then you have a receive. You receive a message from a client. Let's say it could be many things. Handle, some data, message. Then you have some local procedure called handle that does the work. It creates a new state, and then you do loop on the new state. So this thing will keep receiving messages. So it's a lot like what we saw, port object. Huh? So this is like a server. You can also send a stop message, and then this will terminate the server. So this is a very simple server, okay? And the terminate function, maybe you have to do some cleaning up, deallocate some database, whatever. So you do that. So this little bit of code actually is a server in Erlang, okay? But some of this code is generic, and some of this code is specific to your application. So the loop here is generic. All servers do it. Huh? So generic code is something that all servers do, and specific code is something that this one does. So this loop is actually generic. Initialization is generic, but the handle function is specific. Every server will have different one. Okay? So let's try to take this thing and make it generic. So we're going to take this code and turn it into a generic part and a specific part. Okay? So what does it mean? So you have a generic part and a specific part. So what is generic? Generic is what you need always for all servers. So spawning the server, storing the data, sending messages, sending replies, stopping, making more stuff like fault tolerance, other kinds of management things. And the specific part is the actual initialization. What is the data? What are the client requests? The function that handles them. The actual contents, the cleaning up, what you have to do exactly. Okay, so you have two parts here. So we're going to make now a generic server. So there's going to be a piece of code that does this and a piece of code that does the other one. Okay, and the generic one is going to call the specific one, like callback. Huh? You set up the server here in the generic one, and you put in the calls to the specific part, which are like callbacks. Okay? So it's like this. The code now has two modules. There's generic code. This is the behavior. Huh? This actually you don't write. The system gives you this. So this one you don't write normally. But I will show you how to write one so you can kind of see how it works here. Okay? But the real gen server, of course, is doing a lot more stuff than what I show you here. Okay? But it's part of the system, so you don't write it. You only have to write this one, actually, the callback for the specific code. So these two, there's a connection. Okay? There's a callback API. So the behavior module expects certain functions in the callback, and the callback has to define them. Okay? So you have to agree on that. That's important. Huh? So this will give you lots of advantages. So the callback is always standardized. So code reuse. You don't have to repeat the behavior. It's only once. So if you have many servers in your system, all you need is callback modules. Of course, you have a lot less bugs. And all the regular abilities. Let's say you want to do tracing. You want to keep track of all the server calls. You want to do statistics. You want to measure the average time for a request, or the time between requests, or logs, like you want to do an audit. You want to keep track of what happened in the past. All of that is automatic. You don't have to do anything. It's in the behavior module, okay? And you have support for supervisor. So the fault tolerance. So if the server crashes, it will automatically be restarted, whatever, it'll be all very nice. So all of this stuff, you write no code for it. So you see, it's actually really nice. And it's concurrent, of course. This whole thing is concurrent and distributed. Okay? Okay, so you can see that there's really nice advantages. Now I'm going to give you an example of this. I'm going to show you an example with a behavior module and a callback module, and it'll be small, okay? So each of these, the code will be on one slide. So it's slightly simplified, but you can see it's still working nicely. To do that, I'm going to make an example of an application. So this is a very simple server, okay? So I have a little server here, and I have clients. So the clients are like mobile phones, so that's the idea. But and the mobile phones, they need frequencies. They need to allocate like channels. Channel 1, 2, 3, because you have a band and you have many channels. And the two phones have to have different channels. So the frequency allocator here is actually very simple. It just keeps a list of frequencies. 1, 2, 3, up to 20, for example. And when a phone needs a frequency, it calls the server, allocate, and the server sends a reply back, okay, and it tells you you can use channel 11, and this one will maybe use channel 12. And then when you're done, you say, deallocate, I don't want to use channel 11 anymore, and the frequency allocator says, okay, channel 11 is available again. So this is actually a very simple data structure, okay? So the scenario here is with phones, but this server is just keeping track of a list of numbers, which are channels. Okay, so when a phone connects, it asks for a frequency from the allocator, and then when it's done, it deallocates. Okay, and these are all Erlang. Each of these are all Erlang processes talking to each other. So we're only going to look at this thing. I'm not going to show you a whole phone application. Okay, but this thing would be something useful inside a phone system. And actually, the application comes from a real phone system, a simplified version of that. Okay, so it has a very simple API. Okay, if the client needs a frequency, it sends allocate message, and the return is either okay with a number, which is the channel frequency, or error. So remember, this brace notation is a tuple. So this is, okay is a constant. So this is saying, this is like a record with okay and the number, and this is a record saying error, there is no frequency left, all the channels are being used. So if you have 10 channels and 10 phones ask, then the 11th one will get this. And then if you deallocate, the result is always okay. So this is actually not code. This just tells you what is the interface. Okay, when you call allocate, you can get this result or this result. When you call deallocate, you get okay. Deallocate is always okay. You can also start and stop the server. And you have an initial set of frequencies. So for example, 10, 11, 12, 13, 14, 15. So this is a list. And internally, the server keeps track of the ones that are free, still available, or the ones that are already allocated. So it has two lists internally. So it starts with this one, for example, maybe there's 6 channels, 10 to 15, and there's nobody allocated. After it allocates one frequency, then the free list will be 11 to 15, and the alloc list will be 10. You can see it's just a simple data structure, okay? So you see how it's working. So this is simple. It's just an example to fix the ideas. Okay? So that's the server that I want to do. So here's an example execution of this. So this would be interactive. You can run this in your Erlang system. So I do frequency start. This starts the server. I can do allocate. Each time I call allocate, I will allocate another one. So here I'm allocating 6 of them. And this sequence, it will return the last one, if you're on Erlang. So these are all functions. So it returns OK 15, that's the last one. I'm assuming there's 6 available frequencies. If I try to allocate a 7th one, it returns error. I can deallocate number 11, channel 11, saying phone using 11, it doesn't need it anymore. And then if I allocate again, I get 11. You see how it works? So I allocate, deallocate. When I don't need it, I use deallocate, and when I need one, I use allocate. And then at the end, I stop the server. So you see how it works, right? it's clear, huh? Okay, so now let me write the specific module. This is the module that the programmer writes. It's one page, so to simplify, this is the full Erlang code of the module. This is the frequency module. It has two interfaces. It has the external interface, this is the user, and it has the callback interface. This is the one called by the gen server. Okay, so this, you write this, but the gen server module will actually call this internal interface. And these external interface, this is what the clients use. Notice each of these external calls is calling server, 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 server. So these red ones here are interface of the generic module. So you can see the external interface is basically just calling the generic module, huh? And the generic module will call this one. Okay? So these are code you always have to write. You have to write init, terminate, and handle. And the green ones are just doing the work. Allocate, actually doing the data structure manipulation, huh? Key, delete, list operations. Okay? So you see, it's pretty simple, huh? So you have external interface, callback interface. So the external interface always looks like this, kind of, huh? So this is what the client will do, allocate. And when the client does this, it calls the server with these arguments, okay? So you have to write this because maybe you have to write exactly the things you need there. And you have to write also this, the callback interface, and the internal stuff. So usually these two, the violet parts, are very simple, and the internal code, the green code, can be bigger, huh? So this is what you have to write if you want a server. So if you have a big server, most of the code will be the green code, huh? And these two interfaces actually are very easy. Okay? So that's what you have to write. And now I show you what the internal, the generic server. So this one, so this is the generic server module. This one is part of the system, so you don't have to write it. It's there always. Okay? It has an interface here. Start, call, stop, and init. Remember in the previous one we have here start, stop, call. There's also the init, which I don't mention here. Huh? So these are start, call, stop. The init. And the green is the internal part. Okay, so this is a simple server. Huh? It's not doing statistics, it's not doing logging, it's not doing supervisors, it's not doing tracing, okay? The real gen server in OTP is doing a lot more than this, huh? But this one fits on one slide, okay? And it's complete. So the server interface is the violet stuff. The red ones are the callbacks. You see, mod init, mod handle, mod terminate. So the callbacks are the module. So this is the frequency module. This is the one the programmer writes. So these are the callbacks going back to the specific one, okay? So the init, the generic init will call the module init, and then it calls the loop. So this is the server loop, which is part of the generic thing. It gets the request, it handles it here, and it replies, okay. And also it can do a stop, and then it will call mod terminate. Okay, so you see this one is doing the whole loop. So in the previous slide, notice there's no loop here, huh? No loop. So the server loop is not here, huh? Here I'm just showing doing the computation, but no loop. The loop is part of the generic module, huh? It's here. And the real one, if you want to look at the real one in OTP, it's open source, you can actually look at the code of GenServer. It's a lot bigger than this, huh? There's lots of stuff that you don't have to worry. So this is part of the system, okay? So when I start it up, I do init, But then I can start the server, I can stop the server, I can call the server. So these are the three things I need when I'm using the server. So notice when I go back to the specific one, start, stop, call, these are the things that are happening. Yeah? So normally I do allocate and deallocate, and both of them will do server call. Huh? Okay? So you see, so this code is the specific, this is the generic. I make a picture now. This is a picture showing the architecture with the interfaces. So this picture actually gives you a good idea of how the whole thing is done. So I have here the specific module, frequency, the generic module, part of the system, and I show the interfaces. So the client's external interface here, start, stop, allocate, deallocate. Actually, there's a little bit of code here, but it actually calls the server interface. Okay, start, stop, call. This is the server interface. And then the server has a callback interface that goes back here. Init, handle, terminate. Okay, so you have to write this, and it has two interfaces. It has an external interface, and it has a callback interface. Okay? And the server is part of the system, so it calls the callback interface, and if the specific module will call the server interface. So you see how it works? There's two files, two modules, and three interfaces. Okay? So when you use this, all you need to do is write this code. Okay? You see how it works? So that's how the generic, basic idea of how the generic server works. So this thing is completely concurrent, and it will be robust, fault tolerant, and so on. Huh? So the real gen server does a lot of work for you to make your life easier. So this thing actually, with even just writing a small number of lines of code here, it does a lot. So you see, Erlang really makes your life easy, huh? In these concurrent systems. Okay? So that's an example of generic server. So what do you think? It's okay, right? You understand how it works? Now, let me show you now two examples of how the generic server simplifies your life. Two simple examples. And then I will show the supervisor. I will show a second generic one, which is really special for Erlang, which is the supervisor. So the supervisor behavior is all behaviors are using supervisor. So the generic module here will use the supervisor for its fault tolerance. All behaviors will be using it. So I will show you the supervisor, but before that, I will show you two small examples of how the gen server makes your life easy. Okay? So let me show you a simple example with message passing, how the server helps you do message passing without race conditions. So I'll show you the example. Huh? So if you do message passing from one process to another, you can have problems. Let's say you send a message from one process to another, and you want to reply back. But somebody else can send a message back that looks exactly the same, so you kind of mix things, okay? I want to reply from this one, but the other one is sending a message that looks the same, okay? So the gen server will solve that for you. So I'll show you an example of how it works. So this is an example how you don't have to worry about this. So I'm showing it to you now, but the user doesn't have to worry about this. It's solved by the gen server, okay? So here's the example. It's a race condition, okay? So here we have a server, and the client sends a message request to the server, and the server sends a reply. Okay, that's reasonable. But what if somebody else is also calling the client and sends a reply? Well, the client cannot tell which of these is the actual reply, okay? This is a race condition, okay? So here, for example, I send a request to the server, I get a reply, okay? But I cannot tell if somebody else sends a reply to me, somebody else, I cannot make a difference between those two. So that's kind of a mixing, when many people send messages to a client, things get kind of mixed up. So we want to separate that. We want this request reply to be by itself and have no interference from anything else, guaranteed. Okay, so we want to be confident that the reply is actually coming from the server and not from somebody else. So this code doesn't do that. This is buggy, in fact. It's not good. But the Gen server will do it, will solve it for you, and I'll show you how it works. Okay? So the Gen server, internally, it translates it. It uses a unique reference, so like a key, okay? In Erlang there's a function called makeref. When you call it, it returns like a unique value, a key. So this is actually very similar to the names in Oz. Remember we saw the abstract data type and how you can make things secure with the unique unforgeable constants. This is the same idea. So these unique unforgeable constants are really useful for making your system secure, okay? With this, we can really be sure that the response is the reply. So here's how it works. When I do the call, okay, I create first a unique constant, makeref, and then I send the message, but I add this little constant in the message. So the data is actually, I add it to there, okay? So notice this tuple is now a nested tuple. There's more data. This is easy because of the dynamic typing of Erlang. And then the receive will have the ref in there. But the ref is already bound. So the way the receive works is it does pattern matching. It will pick a reply that matches this. But since the ref is already bound here, so it will only pick the replies where you have this value in there. So it will only pick the good replies, okay? And if you do another one, there will be no, if I do another one where I put ref some random constant, there will be no interference, okay? It will never pick this one, never. It will only pick the one that has this special constant ref. Remember, the capital letter means it's a variable, so this is going to be the constant here, ref here. So the receive statement removes the first statement that matches, okay? And notice, if I have a client talking to many servers and getting replies from many servers, there's no interference. Each server, so the client will know which reply is coming from which server. So that means the client can call many servers and there's no interference. You know exactly where the reply is coming from. And this is internal to the Gen server. That means a client can actually be talking to many Gen servers, okay? And there's no problem. You just don't have to worry about it. So the programmer doesn't even have to think about it, okay? But this is how it's solved internally. So the programmer will never even see this, I'm showing it to you because I want to show you how it works. But in an Erlang programmer writing a server will never even see this code, okay? So that's an example of how the Gen server, a simple example, how the Gen server makes your life easy. Many more examples. I'll talk about supervisors a little bit later. Okay, another example is synchronous and asynchronous calls. Okay, sometimes you want to call the server and get a reply, and sometimes you want to call the server but you don't need a reply. It's asynchronous, okay? So the Gen server supports that, both of them. Okay? So a synchronous call waits for a reply, and the Gen server, this is, the name of it is call, server call, okay? And then there's a reply coming back. So this is like the allocate function in our frequency thing, because you send an allocate, but you want to know the frequency, so you get a reply back. So if you use call, you will wait for a reply coming back. But sometimes you don't need to wait. So the Gen server provides another one, In Erlang, it has a funny name. It's called cast. Cast, well, it's like casting is like throwing in English, but it does not expect a reply. So the gen server supports something called server cast. And for example, deallocate in the frequency server does not need a reply. You just deallocate and you're fine, okay? So it could be a cast. That means you don't wait for a reply. And the callback, when you define it, there's actually you don't need to have a reply, okay? So the gen server supports both synchronous and asynchronous calls very easily, okay? So those are just two very simple examples. It does much more, of course, huh? Okay, so you get some idea of gen server now? Well, now let's go to another kind of generic library. Now I want to talk about supervisors. So this is one of the big things of Erlang, where you can build many processes talking to each other, and if something crashes, the supervisor observes it and can restart and make sure it works. Okay, so we saw already a little bit of this in the previous course, but now I'm going to show you the code, how to write, how to make a supervisor, how it actually works. Okay, let me first introduce the ideas. So if you look at practical concurrent systems, there's many kinds of mistakes. But most of them, most faults and errors, are transient. Most of them are like timing or congestion or concurrent startup, and things happen in the wrong order, things, network problems. So many of these can be solved by just retrying. If something goes wrong, you just retry. Many of the errors are transient. Of course, sometimes it's not like that, and you have to do more. But the supervisor handles both. But by default, it will do retrying. So it will favor, it starts by simple strategy. And this is automatic. If you use a supervisor and you're writing a system, it will automatically do this. So you don't have to write any code for this. So you have a set of processes. They are supervised by a supervisor process. So that basically it observes them. And the supervisors have authority. They can do things. They can stop and restart those processes. They can control them. Okay? And notice the supervisors will also be observed. You know, there's a famous saying, who guards the guardians? The guardians are guarding you, but who are guarding the guardians? Well, in Erlang, you have other guardians guarding. So the supervisors is a tree, and on the top level, there is one top supervisor that is not guarded by anybody, but it's extremely simple. So this one, of course, is very, very simple and has no bugs. It's just a few lines, just restarts. So it's actually a tree, okay? And these supervisor trees are implemented, there's no races, okay? When you build a supervisor tree, it's built in a very careful order. Notice that when you actually create a tree, you have to build things in order. If you build a supervisor and there's nobody underneath, then what's going to happen? So you have to do it in a clear order. So the starting is very delicate, but the supervisor generic behavior will do it, okay? So that's the basic idea. Okay, so now the principles of it. So it's a tree, okay, of supervisors, and the leaves are the actual processes running your code. It's a set of supervisor nodes as a hierarchy with a root and internal nodes. So the root, of course, is very important. If you look at some real Erlang systems, remember the system I mentioned last week, the ATM switch that was very reliable and that had a million lines of Erlang. Remember the one I mentioned last week? That one actually has a supervisor tree with just two levels. So it has the processes it has supervisors, and then it has one top-level supervisor, and that's it. Now, usually you don't have to go more than that. Huh? So it's a tree, but it's not a very deep tree. Okay. And then each supervisor node has a strategy. So it observes the processes and has strategies. So Erlang will give you 4 basic strategies: one for all, rest for one, and simple one for one. Okay, so I'll explain a little bit what they mean in a minute, but basically one for one means if the process crashes, you just have to restart that process. And one for all means if the process crashes, you have to restart all of them, even the ones that are working. You have to force them all to restart, okay? And then you have a restart frequency. The number of restarts is limited. So I told you that usually the errors are transient. That means if you retry, very often it will work, but not always. So you keep restarting and it doesn't fix things, then the problem is not solved by a restart and you go to the next level, okay? So the number of restarts per time interval is limited. You can only do a few times, and if you go above that, the supervisor itself will terminate and you go to the next level, okay? So it's like moved up a level. So you want to prevent the case where the process is always dying and the supervisor is always restarting it. That's also bug forever. If that happens, there's a next level supervisor that says, aha, something else is wrong here. And what does it do? Well, then it will do something. Depends on the application. Maybe there's a disk that is faulty, and then the higher level supervisor will reallocate a new disk to the lower code. Maybe it notices that there's a faulty disk or something. Or maybe it has to tell the user. Maybe there's no solution and it just has to inform the technician or the manager, the system engineer. So it depends on the application. But there's no, it will not repeat. So it goes to the next level. Okay? So here's an example of a supervisor hierarchy. So here, the squares are supervisor processes. So they're all Erlang processes, all the squares and the circles. So the supervisor process is just observing the lower ones. Notice it's using linking. Remember we saw linking last time? These are linked. It's using linking to do that. So you can actually program this with what we saw last week. You don't have to invent anything new here. It's using the linking here. So the squares are supervisors. Notice there's a couple of levels here. You have this one, and then you have a higher level one. And here you have 2 strategies, one for all and one for one. Okay? These lower ones are called workers. They're doing the actual work. So here, for example, you have one for one supervision, supervising 2 nodes. If one of these crashes, it just will restart that one, because these will be doing independent work. Okay? Whereas the A, it could be supervising many things. If one of them crashes, it will restart them all. It would force them all to restart, even the ones that are running, okay? Because they're working together. Sometimes you have many processes which are working together, and if one of them has a bug, in fact, you have to restart everything because the others will not be able to continue, okay? So that's how it works. So let me now explain a little bit more about the actual strategies. Here is one for one and one for all, but I'll also explain what the other ones mean. So for one, if any child dies, it is restarted. So if P2 dies, it's restarted. One for all, if any child dies, all the children are terminated forcibly, and they're all restarted. Okay? So those are 2 basic strategies. Here it's like, let's say they all have independent phone connections. So if there's one phone connection that has a problem, you don't break the others, okay? So you only restart that one. Whereas here you have an application working together. Let's say it's managing a database, and they're talking to each other to do transactions or whatever. Then if one of them has a problem, you have to restart everything. Okay. Here are 4 strategies. So 1 for 1 is the one you use if the children are independent. Okay. 1 for all if the children are collaborating. If one crashes, they all have to be restarted, even the correct ones. And then there's a couple of extra ones. Rest for 1. This is all the children that are started after the crash process. It means there's some order between them. Okay, you start one and then another and another, and if one of them, so there's a dependency between them. If a child has a problem, all the ones started later will have problems, so they all have to be restarted. Okay? So all the ones started after, but the ones started before are not involved. Okay? It means there's a dependency between the children. And then there's a version of 1 for 1 called simple 1 for 1. This is where it's all dynamic. So in regular 1 for 1, you start it up, you start all the children, okay? But in simple 1 for 1, you don't know how many children there are going to be. So when it's running, you will keep adding new children, okay? When you need them, like phone connections, okay? So this simple 1 for 1 is used when all the children are dynamic, okay? So this is how it works. But now I want to show you some code here, huh? I want to show you the code of a simple supervisor. So I'm going to show you some Erlang code again. But it's only 1 page. So I made the examples so they all fit on 1 page. Okay? This is a very simple supervisor. Okay? It's very naive. It manages a bunch of children. If a child terminates abnormally, it's restarted. Remember with linking, you can make the difference between normal and abnormal restarts. So if it terminates abnormally, it's restarted. But if it terminates normally, then it's fine. It's just removed from the supervision tree and nothing else is done. So it's not restarted. And if you stop the supervisor, then it will stop all the children. So that you can actually control the whole application by stopping the supervisor. Okay? So we're assuming that nothing abnormal happens when you start up. Okay? So if the supervisor cannot start up normally, the whole startup is aborted. So you don't start up. So we're assuming here for something very simple, that when it starts up, nothing abnormal happens. Okay? And we have a function called apply, which starts each child. Okay? Module function args. This, when you call this, it will start at one of the children. Okay? Basically. And when a supervisor terminates, then the supervisor itself can be linked to other parts, because this whole thing is just one piece of an application. All processes linked to the supervisor will get an exit signal. Okay? So remember, the linking is done through signals. So here's the code. Okay? So let me explain how it works. So this is module my supervisor. These violet is the external interface. So there's a start, the supervisor, the init, and the stop. Okay? So this one will start, so it registers the supervisor under a name, and it starts by calling init. And notice it says traps exit true. Now remember what that means, huh? It means that when the child crashes, that the supervisor will not crash, but it just gets a message. Okay? And then it starts the children. So I have this green function which starts the children. So this is actually a list comprehension in Erlang. So it will go through all the child specifications and it will do apply for all of them. Okay? And then there's basically a loop. So it's a little bit like server. There's a loop, and the loop is receiving exit signals. And it receives 2 kinds of signals, the normal exit and the non-normal exit, okay? The normal exit, it will just delete the child from the child list. Notice the argument of loop is a child list. So these are the normal children, huh? So if it exits normally, it just removes it. If it exits non-normally here, it will restart the child. So here's the restart. And so the new child will have a new process ID, yeah? So you have a new child list, but the child is restarted. And there's a third message stop, and this will terminate. So you have two pieces of green code here. So this one will restart the child, and this one will terminate. So the restart is very simple, actually. Yeah? It looks at the process ID, it picks out the child from the child list, the one with that process ID. It creates a new child with the same arguments, MFA, but the new child has a new process ID, yeah? So it will replace PID by new PID in the child list. That's what you have to do, because when you restart, you create a new process, and it has a new process ID, yeah? And finally, the green terminate one will just do, will just kill the child, huh? So we'll kill all the children. So basically that's it. So that's a very simple supervisor that will just restart children if they exit, if they crash, and otherwise let them stop normally. Okay? So this is, you can see kind of the idea. You're using these exit signals. It's all built on top of the linking, huh? Okay? You see how it works there? Okay? So we want a generic supervisor. So the real supervisor does more. Huh? So again, I'm going to split it into generic part and specific part. The generic part, so you spawn it, you start the children, you monitor, you restart, you stop, and of course you can do statistics. You can determine when the crashes happen, what are the times. Maybe they happen more in the evenings or in the mornings or whatever. And the specific part, which children, the specific handlers, how to start, the dependencies, and also the behaviors. Maybe the children are gen servers or whatever. Huh? So to each of the children, it could be a bunch of processes that is doing, that could be a gen server or something else. Okay? Okay, so that's the supervisor. There's one other thing for supervisors. Remember last time I told you that making robust application is two things. It's supervisor and stable storage. Because when you restart, you have to restart in a consistent state. So where do you find that consistent state? Well, it's sitting in the stable storage, which survives the crashes. And Erlang has 3 different levels of stable storage. So the ETS is the simplest one. It's very simple in-memory data stable storage. Okay? So when a process starts, the ETS table will stay. So the ETS tables are stable storage. It allows restarting the children consistently. So it's an in-memory storage, but it's outside of the Erlang processes. So when a process crashes, the ETS is not affected. Okay? But still, you have to somehow connect it to the supervisor tree. Okay? An ETS table, you can link it to the process that creates it. But usually it's not the worker process. And if you have a supervisor tree, this ETS table is actually linked to the supervisor. Because it's the supervisor that decides what happens to it. So it's observed in the same way as a child process. So you have child processes, but you also have ETS tables. So these tables are also like managed by the processes. Okay? That's just to give you an idea how the supervisor connects with the stable storage. Okay? Okay, so that's all I'm going to say about supervisor. You could say a lot more, but that's all I want to say now. Let me now compare the Erlang approach with defensive programming approach. Okay? So in the Erlang approach, the supervisors handle errors. When there's an error in a child, it immediately crashes. So the child does not handle its own errors. And last time I gave an example of that, of the surgeon who is not operating on himself, unless you're in Antarctica, okay? So usually the surgeon does not operate on himself or herself. Usually there's another surgeon doing the work. And whenever there's an error, errors can be very complicated. You only do one thing, crash. So simple. In Erlang, it's considered very simple. So this, how does it actually work? Okay, so there's been some studies of this. Also, there's companies using this. So after the break, I'll show you how a company has experienced it, Demonware. But first, let me show you some studies. So these are academic studies done in universities. So there's Heriot-Watt University. They compared Motorola for the phones has this thing called data mobility, and somehow it's actually written both in C++ and Erlang. There's two implementations. So the Erlang implementation has 85% less code size. So that means it's 1/6 of the size. It's 15%. And 27% of the C++ code is all error handling and defensive programming. But in Erlang, that's only 1% of the code. Because of the supervisor, it means the application is very simple, okay? Ericsson has also compared the approaches. So there's this switch called MD110. It's written in Plex. So Plex is an imperative language like C, C++, and Erlang. And they show also a very huge decrease because you don't do defensive programming, okay? So the code is actually a lot smaller. So you can ask the question, if Erlang is so great, why isn't everybody using it, okay? But actually people are using it a lot. And they just don't advertise that because it's kind of a trade secret. It works for them, why should they tell other people? But sometimes they do, and after the break I show you a talk given by the technical person from a company called Demonware, which does game software, and it explains how they use Erlang, okay? Okay, so let me make some conclusions now on this. Very basic conclusions, okay? So Erlang language and OTP, so it's message passing, multi-agent. I explained a little bit how that works, okay? Erlang, it's not just message passing though, it has behaviors. So these are patterns for concurrent fault tolerance. The most important ones are the server, the finite state machine for the actual application code, event handlers for important things that happen in the system. Then you have supervisor trees that implement the let it crash philosophy, and stable storage that let you consistently restart. So you have three levels, ETS, DETS, and Amnesia. So the conclusion is that Erlang OTP lets you build highly resilient, concurrent, and distributed systems. And there's many commercial systems using this. Usually they don't advertise, but you can get a long list of companies doing it. Okay, so I'm going to show you one of these companies. Now I'm going to show you a talk which is basically coming from a company called Demonware. Let me go to the first. Okay, so this is a talk given by one of the engineers, Malcolm Dowsey at Demonware, which is an Irish company, a few years ago. This was actually from 2011, but it's a very nice talk, so I'm going to present this. And probably if you are gamers, you have, for example, maybe play Call of Duty Black Ops. If you do that, then you've actually used Erlang in your life, okay? So I'm going to give this talk, but first I make a small break. Donc on va faire maintenant une petite pause. So now I want to talk about games. I want to talk about games. I don't know if you guys are gamers. Some people are gamers and they are passionate about games, and big games are in enormous pieces of software. They are made by huge teams over years. So it's like a big movie. So a big game like Assassin's Creed or something is made by a team of programmers and graphic designers and game scenario designers and everything. So it's like a large movie, okay? So it's a huge piece of software. And here I'm going to talk about a company called Demonware, who uses Erlang for their doing first-person shooters. Okay, so this talk is a little bit different from the talks from my lectures, because it's going to be a little bit technical. So they are going to say what they do in Erlang, and so we're going to talk about supervisors and ETS. But they also will talk about the gaming and the industry and the history of the company. So you get actually some real stuff here. So I'm going to talk first about the history of Demonware and how they started up and why they switched to Erlang. So they actually were writing software and they were having some problems. And I will talk about their architecture and how they use Erlang and what they have learned. Okay. The mistakes they made, the good things they did, what they think is bad in Erlang, and what they think is good in Erlang. Okay, so it's actually a very nice talk because this is the real industry experience. And there's many companies using Erlang, but most of them don't really talk about it so much. But these guys actually presented it. So Demonware. So what do? They make software for multiplayer games, different kinds of software. For example, client-to-client game state transport. If you have to transport game state between clients, that's actually complicated because you need encryption, you need NAT traversal, network address translator. So a NAT actually protects the IP addresses of a company from the IP addresses of the open internet, and you can't go across the net very easily, okay, because of the IP address mapping. There's techniques for that, so they're complicated, so they have software for that, also connection management and peer-to-peer topologies where all the clients are talking to neighbors, so you have a large network of clients, okay? So the NAT allows to make connections across gateways, and peer-to-peer, the clients are actually talking to each other directly without going to a server, and star topology is where there's a server. So you have two possibilities. One is where the clients are talking to each other, the other one, which is called peer-to-peer, the other one is a star where the clients are talking to a server. So it's like a star. Okay. So that's one thing that Demonware does. Demonware also does what's called lobby servers. This is a bunch of functionality that exists in games. So it enables players to meet, arrange games. So a lobby server is sitting next to the game server. So it does matchmaking, it does the leaderboards, who's ahead, it does the statistics, the messaging, the audio, video, websites, friends, and the things against cheating, okay? So that's what Demonware is doing. They were founded in Dublin, Ireland, in 2003, developing middleware for game studios. In 2005, they started hosting the lobby servers, so that means they're connected to big games. In 2007, they switched to Erlang, and I'll explain how that works. And they were acquired, so they were bought up by a bigger company called Activision Blizzard. Usually small companies, if they are successful, some point will they get bought by big companies who need the functionality. And in 2011, when this talk was given, they were one of the world's largest game service providers. And even though they're the world's largest, they had only around 60 employees. in Vancouver, in Canada, and in Dublin, Ireland. Okay, so that's the history of Demonware. This is an example of some games that use Demonware software. So all the Call of Duty ones. So maybe some of you have played Call of Duty. I don't know. So raise your hand if you played Call of Duty. Wow, lots. So you've run Erlang. You've run their software. Okay. So these guys are used by Call of Duty. They're also used by other games, Guitar Hero, Transformers, whatever, bunch of other games, and more games, okay? So they provide very important services for many different games, okay? Demonware. So see, this is a real company doing stuff that's important, okay? So what do they actually do? So the whole online infrastructure for Call of Duty Black Ops, in 2011 it was the best-selling game. I don't know, probably not anymore. 4 of the top 10 games, and it's by 2 million concurrent users, 150 million registered users. So concurrent means they're actually online at the same time. Okay, that's a lot. Okay, 2 million are connected to this thing at the same time, and it's cross-platform, running on many things, okay? In those days it was PS3, whatever, but now it's probably advanced. But here in this talk, they explain a lot of what they do in Erlang, so that's why I'm doing this, okay? Now, how did they get into Erlang? Well, they're building software, so their software originally looked like this, not very stable, and now it looks like this, okay? That's sort of the picture, but they explain it now. So how does it start? It was in 2003. Students from Trinity College Dublin, you see, university students started it, so you guys could start a company. They wanted to sell client-side network middleware to game studios. So they started building something, but in the beginning it was hard, okay? A lot of polite interest. It means people and companies said, yeah, looks interesting, goodbye, a few customers. They wanted online servers, not middleware. So middleware is software you put in between the network and the application. But that's not what they wanted. They wanted servers, so full things talking to other things. Okay, so the company started making a server, a lobby services platform. Okay, and in those days there was Xbox Live, and they were kind of copying that, and PlayStation needed something. So they started working on that, okay? Lobby services platform. And in 2005, they built their first server written in C++ and MySQL. So MySQL, MySQL is a database a large high-function database. It was a homebrew, single-threaded, not concurrent. And whenever you have a service, you go into sub-processes, so process operating system, but not Erlang. And all the application logic was in C++, and that used the MySQL database. Okay, so this did not work very well. One operating system process, like Mac OS or Windows, per user is very bad. Okay, you cannot have so many of these, so they had a maximum of 80 concurrent users, which is not much. And then the system would not go more. But their first game, luckily, there was not enough, it was a very small game, so they didn't get this limit. Also, C++ crashes a lot if the code is immature. And the guy says the code was immature, and it crashed a lot. Okay. So C++, it's hard to really make it reliable. You have to work very hard, okay? So that was their first thing. So now they tried to do better. So the next one, where they would use Python in addition to C++, they rewrote all the C++ business logic in Python. They maintained a pool of OS processes, so they would not create them. They would all be existing and using them. The core server was a C++ program that handles thousands of concurrent connections, okay? And it did many things: encryption, decryption, dispatching, asynchronous messaging, some cheats like duplicate login detection, licenses. So this kind of worked, but there were still problems. This is a very concurrent program, and C++ is not a good language for doing concurrency. It's very hard, and the code is very complicated and impossible to maintain. The error handling was poor. The debugging was very hard. They didn't really have metrics. That means they want to have statistics of how the thing is running. They didn't really have it. And scalability, they couldn't actually make it grow bigger. Okay? And also, whenever they had to change the configuration to update the software, change even the configuration of how it works, they had to disconnect all users. Oh, that's terrible. So they change something in the system, and you're playing a game, they just disconnect you while they're doing that. It's a maintenance operation, this. So that's very bad. You want the software to keep running even when they update things, okay? So remember, we saw that Erlang actually has support for that, okay? So this was 2005, 2006. In 2007, there was a former developer who looked at this, and he rewrote the C++ server in Erlang. And in a few weeks, he just got a prototype. So this was like a free Electron. So the team was not using Erlang, but one of the guys who we used to be with the project, he knew about Erlang, he rewrote it in Erlang. He got a prototype in a few weeks, and after 4 months of development, it actually started being used. It was solid enough to be used, and it went live with real users in 2007. And they noticed it had a lot of good properties. It didn't crash. It was you could reconfigure without affecting the clients. Amazing. You could change how the software is configured, and the clients could keep on playing while you did it. You had logging, administration tools, and far fewer lines of code. Okay, so this was very nice, but now I want to go into a little bit of detail. How come? How does that happen? Okay. Okay, so let's set the stage. So we're in 2007. Demonware is doing not so bad. They have many customers: Activision, Ubisoft, Codemaster, etc. They were acquired by Activision. They were supporting some big games here. But still, they did not have a monster blockbuster yet. Okay, so they had 20,000 concurrent users, but that's not actually a monster blockbuster yet. And they were a small company. They had 11 developers, 3 operations people, and 3 managers. So that's kind of still a small company, okay? And then, in 2007, a blockbuster arrives. So this was Call of Duty 4, Modern Warfare, okay? It was the most popular game on the PS3, which was new in those days. And it gave those guys a lot of pain, okay? The people playing it were very happy. But the number of users was growing for 5 months. And whenever it gets bigger, they got a bottleneck. They found a problem, another problem, and another problem when it's growing. Lots of outages, late nights, so a lot of stress for the company, okay? So when you use the game, you don't notice that, but for the company, it was a crisis. So the small company had to grow up, okay? And they managed to survive and grow. And because of Erlang, they were able to grow it. And without the switch to Erlang, it could have been a disaster. It could have crashed and burned. But no, they managed to grow with the blockbuster, okay? And after that, they kept growing. So now they go from 20,000 to 2.5 million concurrent online users, 50,000 requests per second, okay, which is a lot. 1,850 servers spread across many data centers. It's a big thing. It's big, okay? 60. All of this, they only need 60 people. Also, they became very smart. They grew in competence. And they added many features. Okay, standalone components. But now they have many, many things added. Okay, so that gives you the stage of this thing. Now, let me explain how they're using Airline. Okay. So the Airline is used as the core server. So it manages hundreds of thousands of concurrent TCP connections. It schedules tasks for Python. It does metrics. So SNMP is a network management protocol for monitoring the behavior of the networks. It has a presence server. So this is using the Manisha server. It does message passing, of course. It has other kind of functionalities. There are other servers, transient in-game data, testing bandwidth, the ranking, the leaderboards, okay? So it's used for all the concurrency stuff and gluing sequential code. So they had all these little sequential pieces of code, like written in Python, and the Erlang was on top, was connecting and gluing everything together, okay? So, for example, in TCP connections, you have 2 Erlang processes per connected users. They're using a simple one-for-one supervisor. So remember, we saw that. It means you have dynamic children, and you only have to restart each child when it crashes. Okay? The work, the actual communication is done in Python processes, but there's a supervision tree on top. Okay. They have some optimizations, task queues. They can update Python code without affecting the users. So the Erlang is actually managing, like you have a piece of Python making the communication, and you can update to another piece of Python, and the Erlang allows you to do that without affecting the users. Okay. It also does periodic tasks. So that's one thing they did. They did what's called a presence server. So in games, a presence server is important because it means that you cannot be logged in twice. You cannot, there cannot be duplicate license keys, only one. So really a consistent snapshot of who is connected in the game. So you have these big distributed games with many, many online players concurrently. And a player cannot be logged in twice. That's logical. But making sure that you have that is actually hard, okay? Because it's very big and distributed all over the world. You also have in-game messaging, but the gamers can send messages. This is using what's called fragmented Manisha, okay? So fragmented Manisha will actually implement the Manisha data in different parts. So this scales very well into Rust, okay? And it's running on clusters. One of the clusters is 16-core Dell RC10. So this is a cluster computer. It's not a home PC. This is a cluster where you have, this has 1,000 cores, okay? So it's big. That's their biggest cluster, okay? Erlang has libraries for network management, SNMP, and they use it for monitoring the users, requests, the timing, the number of logins, logout, the reasons for disconnecting. So basically they're monitoring this whole big thing with millions of users. And the most important function they call is ETS update counter. So ETS is an in-memory database, and you can update values. So counters are very important. You're counting. So this is very important. So they're keeping a lot of statistics. So this is one of the functions they call at the most often. Okay, and then they generate these big metrics. So you have, this is just a snapshot. You have these graphs of how the system is behaving. Okay. Okay. Also, there's the notion of configuration. So each game has a configuration. So all the different parts of the game, how they're connected together, how they're spread over the world. And the configuration sometimes they have to change. You have to set it up when the game is starting, evolving with time. And in Erlang, they have all the configuration codes done in Erlang. You can set options, instantiation here, cross-cluster upgrades. You can upgrade, roll back on failure. If a part of the system fails, you can roll it back. That means you can bring it back to a previous consistent state, okay? And language agnostic. That means the Erlang code controls modules written in other languages, okay? Okay, and then you have something called Puppet integration. So this is, I'm not an expert at Puppet integration, but it's an approach for operating software independent of where it runs, okay? So the configuration is trying to be simple and painless. Now, they have a console. That means you can actually log into this system and see on your screen graphs and things moving like a dashboard, what's going on. This is using YAWS. So YAWS is the standard Erlang web server, yet another web server, YAWS, which hides manuals, which is very well logged, very concurrency. So it's used for the console live debugging. So if there's a problem, you can see the problem on the running system with real users, okay? You can remotely do many kinds of management things. You can manage, see how popular certain features are, message of the day, okay? So you can actually do a lot of the management of the system remotely while the system is running, okay? And they have a lot of game-related services. The leaderboards, who is the best, who's doing well. So these are all ranked in real time with 15 million users. So this is using ETS. Then you have this trees module here. So you have basically data structures. And you have also in-memory key value store. So key value store is like a hash table, it's mapping things. And this allows you to group users in categories and do other things like presence. And you can do testing, bandwidth. Each client will get an estimate of the bandwidth. So you see there's a lot of things going on here. Huh? Okay? Okay. Now let's go into more of the technical stuff about how they're using Erlang for this. Okay, when you write Erlang code, this is what they learned. The core data types in Erlang: I/O lists, records, not tuples, okay, binaries, bit strings, the refs, atoms, use them. So all the core data types are very important. Think functionally. So this is this industry guy saying it, okay? So it's maybe when I say it, you don't believe me, but when this guy is running a company where you have millions of concurrent users, and it works, his software works, so probably something there. Think functionally and concurrently. You have to think concurrently. Tail recursion, functionally structure, high order. New processes are really cheap. People who don't know Erlang, it's hard to believe that an Erlang process is very, very cheap, but it's very cheap, okay? And simple things can go a long, long way. Okay, so those are basic things. Now, OTP. So I mentioned behaviors, Gen servers and something. Their experience is use it as much as you can, religiously. Gen servers, supervisors, never do send and receive explicitly. Always go through OTP. You see, if you use OTP, then you have abstraction on top. You have behaviors on top. Never send and receive. That's very low level. It's like go to, It's very low level. Don't do it. Never run spawn yourself. Let OTP do the work. Let the behaviors do the work. okay? And whenever you have a component that's reused, turn it into an OTP application. So use these OTP applications, okay? And the modules should be small, no side effects. Try to keep the modules sequential. The modules are not concurrent. The concurrency is done in the behaviors, okay? And not by the users in the modules they write, okay? So the modules will be either your modules are sequential or OTP behaviors. You can see the guy is writing behavior with a U. It's coming from Ireland, okay? And then there's the rule of KISS. Keep it simple, stupid, okay? That's what KISS means. Avoid internode dependencies. Dependencies are very bad. So a node, which is like a machine, with an Erlang virtual machine, might depend on another one. That's very bad, but you can do it easily in Erlang, but don't do it. Okay? Expect problems. High latency, internode network issues. Expect the bad things will happen, okay? And make sure the airline can handle it, okay? Don't do inter-process dependencies. The processes should not depend on each other. Be very afraid of processes which rely on each other. Use casts. Remember I mentioned cast before the break? A cast is asynchronous. You send and you don't wait for the reply. So the call waits for the reply. But that actually makes a dependency. You see that? When I call, I have to wait for a reply. So I'm dependent on that reply. And if the reply does not come, I have a problem. So that's a dependency. So you should minimize calls and use casts instead. A cast is you send a message and you don't wait for the reply. So you have no dependency there. Okay? Dependencies are very bad. Okay? So that's lessons they made. Okay. Another lesson is the notion of a bottleneck process. In a big Erlang program, there's many processes, but some of them will be kind of overloaded. They're called bottleneck processes. It's because many messages are going to this one. Okay. So what do you do if you have a bottleneck process? Well, instead of having one, you have to make a pool. So you make several of them. And so the messages are spread across. Make sure that the work is not done there, but somewhere else, okay? Also, purging the message queue. Maybe it's possible to get rid of some of these messages, okay? So a bottleneck process should not do a lot of work. It's getting a lot of messages. It should pass the messages to other people. Okay, and then there's some other process if it's doing actual work, computation, okay? Make sure it's left alone. Don't overload it with messages, okay? And make sure it decides when it wants to do more. So this is very important. That means the system is lazy. You see, what it means is you don't give work to a process, but you wait for the process to ask for more work. That's also for humans, huh? If you're doing work and someone comes into your room and keeps giving you more work, so your huge pile is growing, it's very bad. But much better is if you do work and when you finish, then you ask for something else. So it decides. So this is very important. So the basic structure of the system is a lazy, demand-driven. You see that, huh? It decides when it wants to do more. The consumer decides when it takes more. Okay? So that's the idea. So message and work processes, this is how to manage them. And in Erlang it's easy to do that. Huh? Another lesson is ETS. So I mentioned ETS, I mentioned stable storage, and you say, yeah, whatever. But ETS is very important. Use it. Okay, it's extremely fast. It's linked to the processes, to the supervisor. Remember I mentioned this, huh? That means it's automatically cleaned up as part of the supervisor management. You don't have to worry about cleaning it up. It's automatic, okay? This will avoid single process bottlenecks because it's very, very fast, okay? Also, it has limitations. ETS is very simple. If you want to do complicated things, don't implement it. Don't reinvent Manesia, okay? If you need to do very complicated kinds of queries, use Manesia and not ETS. So ETS is a very simple, stable storage, okay? Also, the complicated one is Manesia, okay? ETS simple, Manesia complicated. It's a very powerful database. It handles many things. It's distributed, it handles fragmentation, it's atomicity, it can do transactions, and it can do arbitrary, complicated Erlang terms. So this Demonware really likes Manesia, okay? So that's one thing. But it's complicated. It's a very complicated application, Manesia. It's a part of OTP, but it's complicated, okay? So don't use it except if you need it, okay? So Manesia is like a traditional relational database management system, okay? It's powerful, full of features, but so complex you'll swear and pull out your hair out at times, okay? I don't know if the guy is bald or not, but pulling your hair out is not a good idea, okay? But so the other one is ETS. So you have this two extremes, huh? Extremely powerful but complicated, and extremely simple and fast, but sometimes it lacks what you need. So you have to play with the two, okay? Manesia and ETS, okay? Testing. Testing, super important. So you've done testing in your project, huh? And maybe you think testing is a pain, but testing is important. Automated tests, testing full clusters, and what they do is a fault injection. What they do is they will kill a random Erlang process of this big application. They will pick one and say, kill it. And the thing has to keep working, okay? And this is a really good way of testing, huh? Take your program and kill a random process, and it has to survive, okay? It's nice. It's nice, huh? Approach, huh? And Erlang has tools called Dialyzer and fprof, so those are important. And then heavy-duty end-to-end load tests. So basically they run their system with 2 million simulated users, the actual system, and they run it heavy, and it has to work. And with fake users, simulated users, this is also important, okay? So you see, testing is very serious here, huh? To make it work, yeah? Okay, and then there's more things, miscellaneous things. Keep your clusters apart. Process priorities. Notice processes have priorities. Some of them are high priority, low priority. But 10,000 small guys can kill a big guy, okay? If you have 10,000 low priority, unimportant processes, and they're running badly, inefficiently, this will clobber one important, vital one. So be careful about priorities, that you don't overload the big guys because there's too many small guys, okay? Hot swaps, code replacement. This is amazing, of course, but don't overdo it. Often more effort than it's worth. This is still hard, kind of. Don't do too much. Then things like kill switches. A kill switch is where you can actually shut down part of your system by pushing a button, okay? Metrics, graphs. You have to see what's happening. So you have to have graphs like microscope, telescope in your system, huh? Remote shells really go into your system, okay? Let's see, so where am I? Okay, good. So these are all good pieces of advice, right? What do you think? Huh? What do you think? It's interesting, huh? Okay, another lesson. This is psychology. Be polite. It means even in Demonware, they have 60 people, but there's only 3 or 4 who are doing Erlang. There's a huge amount of software, and many of the tools are written in Python, C++, still, and it's controlled by Erlang. Your coworkers don't care about Erlang, So the guy writing the Python code, he doesn't care about Erlang. So the guy writing Erlang code, he talks to the guy with Python. So you're living in a multi-language environment, okay? So Erlang people, they tend to be kind of religious. Erlang is it, you know? So the idea is don't be too religious, okay? Don't force the user to use Erlang syntax or read Erlang or understand Erlang. Just keep yourself neutral, okay? It's still a niche language because even though it's controlling all the concurrency, the actual computation is often done in other languages, okay? So it's doing the fault tolerance and the concurrency, but it's still living with many other languages, okay? And now the things that are bad about Erlang, we're missing some things we'd love to see in Erlang. First of all, amnesia, they would like it to be better. Network outages, node crashes, doesn't handle them good enough. Maybe Cassandra is a cloud database. Maybe they want connection. Things like functionality, like eventual consistency. This is a database functionality. Cap theorem, this is a database thing. It means that you can't have your cake and eat it too. So I won't explain all that, but they want more functionality, okay? They want more automatic cleanup logic, okay? They want to keep the data separate from the process responsible for it. So you have to keep things separate, make the cleanup simple. Okay, OTP. So you have these low-level functionality. Receive, send, link, spawn. This is like machine language. Actually, real Erlang programmers will never use those. I showed you those, okay? But real Erlang programmers will use behaviors, so you never have to call them. It's like machine language, assembly language. So you don't use them. They also want more flexible supervisor trees. They want more specialized ones. More restart. They want more. Okay, you give them the part of it, but they want more restart strategies, more dependencies. Okay. Okay. They want it. Also, they want some processes to respond quicker, so they need certain kinds of priorities. Okay. Okay, so here's an interesting point. Erlang is very specific. It's very good for hard concurrency, so large system, million of users, but usually you don't actually do the business logic, the computation in there. You don't do machine learning in Erlang, okay? So you have to connect Erlang to other languages. So this should be easier. So this maybe is not easy enough, they say. Okay. Then they have some comment on static typing. Okay. So dialyzer is actually a type analyzer. It runs, it tells you if there's errors in your program before running it. Okay. Which works very well. But they want more static typing. But they also want more dynamic features. Okay, so they want more of everything, basically, yeah? Okay, let's see, what time am I now? Okay. Okay, and now the learning of Erlang. So this is the industrial experience. So in Erlang, hard things are possible, but easy things are maybe not so easy. So moving to Erlang is a big commitment for a company that's not using Erlang, okay? So tutorials, coding styles, standard guides, documentation, friendly syntax. So now there's actually something that's going this way. So you maybe have noticed that there is a language called Elixir now, which is a language that has a syntax like Ruby, so more standard syntax, but it's using the same virtual machine underneath, Beam. And this has a very big community. So Erlang and Elixir are now both living together as concurrency languages. So this kind of solves some of this, and Elixir is actually quite successful, okay? Okay, what do they love about Erlang? They love many things. Effortless concurrency, complete solution for hard concurrent problems. If you have a hard concurrent thing, do it. Open source, you can look, everything is there. Remote shells, robust and reliable. You can have systems that stay up for months on a time without crashing. Okay, that's not bad. Okay. Black Ops, 24-hour stats. Okay, so they have. It's maybe hard to read. Okay. Who said gamers are lazy? For the last 24 hours, all the players in Black Ops have killed 323 million opponents, more than the entire population of the USA. They shot 28 million enemies in the head. They used 65.3 Hummer H2s of frag grenades, okay? They shot crossbow bolts with a total length of the Great Wall of China, okay? So gamers are not lazy. Look at that. They kill 300 million opponents. Not bad, huh? In 24 hours. Okay. So that kind of finishes it. So in Demonware, Erlang helps make tens of millions of gamers happy. If gamers are happy, then they are happy. Okay? And so Demonware likes Erlang. And this was in 2011. I don't know if this is still true. So this talk was given in an Erlang conference called Erlang Factory London. And so they were talking in front of an audience of Erlang people. And so they were looking for more Erlang people. Okay. So that's it. Let me stop there. So that gives you an industrial viewpoint on Erlang. So you can kind of see the good and the bad. So if you're ever writing big things that are games, big concurrent things, these guys show you can do it. Erlang has the muscle, but you don't probably want to write everything in Erlang. Some things cannot be done so well in Erlang. Okay? Okay, thank you. So let me stop there. So what do you think now? You're going to run out and start using Erlang for your big system? Notice these guys. They were at university, and they made a company. Trinity College is a university, and they made a company. But they started by using C++, Took them years to figure out that it was not a good idea. Okay, je m'arrête là.